Hello, it's Dr. Ron England. This is Module 5 of EGN3443, which is Probability and Statistics for Engineers. Today we're talking about continuous probability distributions. Last module we talked about discrete probability distributions. And you would think, well, what's the difference? Well, discrete and continuous. And you should know what discrete data is and what continuous data is. Okay, I'm just not going to explain it right here. You should by now have the concept of discrete and continuous. If not, hey, you know how to get in touch with me. So for my students, but if you saw it in the last lecture. So the concept here, though, is we do still have the good. We had a probability mass function when we're talking about a probability distribution function. And the probability distribution function is extremely useful in looking at how data fits the different types of distributions. Now, the key property of the probability distribution curve is that the area under the curve always equals 1. Now, you think about this, it's a continuous distribution. So unlike when you were talking about discrete distributions, where you take all the possibilities, because there's a discrete number of them, and you add them all up, and they're 1, well, there's no longer these discrete values. It's continuous. So it should make sense that it's a different way to calculate, to look at the actual, the curve, and the total area under the curve, okay, is 1. Now, if you look at the individual values in the function, you'll notice that there's some different nuances of the functions, of the values. I'm not going to go into those yet because I really want to show that by example. And calculating a specific probability, well, one is you got the ability of calculating an individual probability, but that really doesn't make any sense in a continuous probability. You think about that. Unlike rolling a die where you say, what's the probability of 6 or 5 or 4? Well, those are things that discretely happen. But in a continuous probability, when you're talking about continuous probability functions, well, 6 could never occur, but it still has some sort of probability associated with it because the values are continuous. What you really want to know is what's the probability of something between two values, which is really looking at the area under the curve. But what you really want to find, if you want to find something between two values, is looking at the area under the curve between the first value and the second value. So you may want to say, what's the probability of the value being between 1 and 2? What's the area of the PDF curve between the values of 1 and 2? So let's just look at a really simple example here. Okay, these are typical probability distribution functions of the most common, the good old normal distribution. So if you look at this, you'll see that we're looking at the values between 40 and 65. That x is 40 and 65, and the probability density, PDF probability density function, is the y-axis. So the probability is the area underneath this curve between those two values on the curve, and that's actually looking at the probability density of a normal distribution. Okay, and I just picked one at random. And over here you can see the exact same thing on the cumulative distribution function, which again is essentially the same as what you had seen with the cumulative into the discrete value, but what it's doing right now is it's accumulating the probabilities. It's cumulative distribution function, and you basically, to find the probability using the CDF, you take the value, the cumulative probability at the bigger number and you subtract the probability at the lower number from the CDF, which should still give you the same value of using the PDF. So in other words, the area underneath here, underneath this curve, okay, is the probability. If you take the cumulative distribution function, you can get the same value by subtracting at the upper and the lower from the upper. So it's this one minus this one, which also gives you the same value, which is the probability. This applies to all different distributions for their PDF and their CDF, okay, for all of them. This is just an example of a specific distribution function, which is the normal. I said a lot of that really slow because I really am trying to emphasize the key points of how to do this. Okay, now, the other piece of this is how are you going to calculate these? Well, you're going to use the Python functions, but you're also going to always be responsible for giving the correct visualizations of these in your reports. So, we looked at just a probability distribution function, or probability density function, and now we're looking at the cumulative, which is, again, the accumulation of these probabilities that you just saw in the last one. And if you wanted to, you can actually, express it mathematically, okay, which is that it's the function, it's the derivative of the function df dx. Okay, it's that simple. It's not. I really don't think anybody's going to have a real problem understanding the relationship between the probability density and the cumulative density, the cumulative probability, because it's simply just adding these guys up. Okay. All right. Then let's see what we are here. Let's move forward. Now, where do we apply this? Well, we just showed the actual calculation pieces. There is a definition here that we use in engineering. So the probability that the value is the probability is less than or equal to x. That actually is kind of important in the CDF because, like, when you're looking at the curve, when you pick up one of the values off of the CDF, what you're saying is, what's the probability here of it being between, this value and this value? But what's also looking at it is what's the value where it's between 0 and 1, or 0 and the specific value. In other words, what I'm saying is you can read this curve in two different directions. So if you say, well, what's the probability, what has a probability of 0.5? Well, what has a probability of 0.5 is it being between 0 and 50 by reading these axes. I don't know if you can read the axis. That's 0, that's 50, and then the 0.5 is right here. Okay. That's the same thing that we're saying right here. And if you're looking at an interval, okay, you're taking the difference between the higher one and the lower one based on probability. And again, it can be read in both directions. Okay, going back to the curve. Probability being on the y-axis and the values being on the x-axis. All right, that's what I'm saying with that. That's what those equations say. Now, how you're going to calculate these? Well, you're going to basically be using the computer program, but you kind of just want to know what that is doing. The definition that I was going to point out to you is the survival function, which is basically looking at what's to the right side or above in the probability. So from 0 is the cumulative distribution function goes up. You can see that those values go upward. Everything up here and over here is looking at the survival. You've got survival probabilities and quantities on both the y-axis and the x-axis. And they're all mathematically related to the original distribution function. But again, this is going to apply to multiple distribution functions. We've just looked at an example of the normal distribution, but there's other distributions. So the basic distribution you're going to use is the normal distribution, and the probability density function is given as, this is the classic probability distribution function of the normal curve, the bell-shaped curve, the normal distribution, the Bell distribution. It's got all of these names, just pretty much you need to know when we're talking normal distribution. But the thing is not everything actually fits a normal distribution perfectly. We got other distributions that we've got to look at. But a lot of stuff fits the normal distribution and fits it very well. Now, central limit theorem actually says that pretty much as you get more and more data, everything gets really close to normal distribution. Okay. Well, let's talk about that when we get to the central limit theorem, which, by the way, yes, is later in one of the later modules, but it's not in this one. Right now, let's just talk about the distributions that you're going to be dealing with. Now, one of the well, let me do to the next slide, because this I'm going to tell you. I can say the empirical rule, but here's a good way of looking at the normal distribution. Now, when we're talking normal distribution, we're really talking about the mean and the standard deviations away from the mean. All right. Now, we like to talk about that in terms of z-scores. And the reason for that is it just gives you a much better ability to visualize the normal distribution. So what really is a z-score is essentially looking at how many standard deviations are you away from the central, the mean. We use it all the time in quality control. You would say you might be looking for a z of 3. And a lot of times when you're talking about a z of 3, you're talking about a z of 3 on both sides of the center, but it can be specific to either direction. So if you're looking at, say, a z of 3, what you're really saying is that 99.87% of the data is below that value, whatever the value of that z is. And if you look at this closely, you'll see that, like in z minus 3, that's the left-hand side of the bell curve, only 0.13% of the data is below it on that side. Now you can see in this case, if you look at those numbers, you'll say, oh, it's actually symmetrical. Yes, it is. It is symmetrical. So the z of 0, which means that you're no standard deviations away from the mean, means that half the data is below and half the data is above. So if somebody says, I'm 1 standard deviation away from the mean, maybe in height or weight or intelligence or something, okay, well, it depends on which direction they're going, but if they're 1 standard deviation above the mean, they're saying that roughly 84% of the other people are below them. If they say that they're 1 standard deviation below the mean, they're saying that roughly 16% of the people are below them. And if they're saying that, then they're probably not, if they're bragging about being z minus 1, they're probably not bragging about their intelligence anyway. Just saying. Now, normal distribution is used everywhere. I would just give you ideas and say it, but it is used everywhere. But realize it's not the only distribution. This is a continuous distribution. It has a specific shape. It has those parameters, which in this case you can say are the mean and the standard deviation that defines the curve beautifully. Okay, but it's not the only distribution, but it's one that shows up in lots of different types of measurements. Now, you have probably heard of 6 sigma. Read this on the left-hand side. Okay, 6 sigma methodologies leverage this to achieve 3.4 defects per million opportunities. Well, what are they saying? Well, they're saying that there's 6 standard deviations away from the mean and that they're on the good side, that there's very, very few defects. What they're doing is they're going back to this and they're saying, well, what is if z is plus 6 or z is minus 6? It depends on which way you're looking at it, whether you're looking at it defects or successes. Okay, either way, the intent is the same. That's what your goal is, to get to that high level of quality, but it's basically a measure of standard deviations away from the mean in a normal distribution, or actually whatever distribution the data of what you're doing follows. So let's talk about some other distributions, because you've seen normal, normal, you've had it. These other distributions follow the same concepts, but they have different shapes. So one of the distributions we can talk about is the exponential distribution. And if you look at the PDF, you'll notice it's exponential. And you got this lambda, and the lambda is the rate parameter. And if you look at it, it really is the parameter. That's it. Now, what is this useful for? Well, one of the things that it's really useful is measurement of lifetimes. And what I mean by lifetimes is mean time between failure. How often does something fail? Because it tends to fit this type of distribution. It may not fit it exactly. We're going to talk about that in just a minute, but it does fit it pretty well. Basically, you're saying that in the early days, there's not a lot of failure, and as you move further in time, you have a higher probability of failure, and it follows an exponential rate curve. Now, if you really want to know something that follows it really, really well, is radioactive decay. It follows it almost perfectly, because that really is how we model radioactive decay. But there's a lot of other things that follow this. There's 2 abbreviations in engineering you need to know. MTBF, mean time between failure, MTTF, mean time to failure, and you really kind of want to not get those confused, because we're really talking about, failure to failure, but this does fit exponential distributions quite well. So what does it look like? Well, if you look at the plot on the left, and I'm going to actually jump back to that normal distribution. You notice how the normal distribution, the PDF looks? It goes up and then it goes down. And the cumulative goes up with this nice, beautiful shape. Well, what does that look like in an exponential distribution? Well, the exponential distribution looks like an exponential decay. That's what it looks like. Okay? And if you look at the probability density function, you'll see that it actually plots out as this decay. It's useful for measuring mean time between failure, and you can actually plot targets and mean times between failures because they fit this distribution relatively well. So, if you're trying to actually, and remember, what is the actual probability of something? When you're looking at the actual probability, well, it's the area under the curve. So if you were saying, what would be the probability of a mean time between failure of X hours and Y hours, you would look at the area under the curve of this PDF curve between X and Y. If you wanted to know the mean time to failure specifically, then you'd look from 0 to the value that you're looking at. So in this case, what you're saying is that the red shaded area is the probability of failure before the value that it goes to. In this case, it's 800. And the green shaded area is the probability of survival. And many times what you're trying to do is you're trying to say, I want to get a low probability but you're gonna, and when I'm talking, right now I'm just looking at this specifically as a distribution, but you have to develop a strategy for, let's say you add maintenance to this and watch what the modifications are, or actually trying to make sure that you have a maintenance that occurs before the typical failure rate, looking at the failure before a specific time. Hopefully I didn't confuse anybody with that, because it's not that really that hard, but if it fits this distribution. Now, one of the things that's really useful if you've got this exponential distribution, by the way, the cumulative distribution, the cumulative failure probability is the blue line right here. It is your cumulative distribution function, and the green line then becomes a reliability function, because it's the opposite. It's basically flip that over. All right. Now, this is useful, but what actually is really useful if you have this is making this. Okay, this is a maintenance strategy. And what it does is it takes different maintenance intervals and it simply looks at the failure probability and the survival probabilities. It kind of discretizes it. It looks at it comparing at these specific intervals. And that becomes useful for decision making. It's not any different from what you saw on the previous slides. It's just putting it into a format that allows you to actually look at it in a way that's very useful. Now, this is the exponential distribution. Not everything fits it perfectly. And so we're going to look at another distribution that's useful called the Weibull probability distribution. Now, in the Weibull probability distribution, we actually have some more parameters, but there's a specific parameter that we're going to look at here. So and you notice that there are more parameters. You've got a K and you've got a lambda there, and the K is the shape parameter. It's also sometimes you're going to look at it as beta. And lambda is the scale parameter, and the scale parameter is what you actually see in the exponential portion of the function. If you look at that function, you notice that there's some parameters or some stuff, and then there's an e to the negative x divided by lambda. Well, that looks a lot like the exponential function that you had before. Okay, well, what this allows you to do is give you more flexibility in how this can be used to fit. As the K approaches 3.5, it looks a lot like a normal distribution. Okay? And the values of K change the shape. At K equals 1, and you can show this by looking directly at the function itself. At K equals 1, it is the exponential distribution. So it can take on more complex shapes, which means that it's more general, which means that it can fit more types of data. So there are a lot of different types of measurements that fit Weibull distributions quite well. And remember, your goal is to predict better. Do a better job of predicting. So knowing that the Weibull distribution can actually is a more generalized case of the exponential distribution with more parameters, you can measure more things. Now, in the Weibull analysis, one of the pieces is the collection of data and the estimation of the shape parameter. That K has to be estimated. So this is a lot easier to look at if you look at it in terms of an actual example. So what we're going to do is this can be any component failure, and you're going to find that some things just fit the Weibull better. The aging of components, taking away things like corrosion and things like chemical degradation, which fit log normal beautifully, the Weibull tends to be a better way to go. And it's also a lot easier to visualize if I plot these together. So in this plot, you're going to notice that there's a purple line which is the probability distribution function for a sigma equals 0.5 in that probability distribution function there. And what I actually have here showing this is that there's some Weibulls plotted on this, okay, and some of them look like they're very close to the log normal, and some of them have different shapes for different betas. The best way to figure out if you want to use, let's say you do this and you say it really doesn't fit my exponential. Oh, I'm showing the log normal. I should have shown the exponential. Why did I show the log normal? Okay, well, I'm going to get to the log normal in just a second. I should have plotted the exponential, but I would definitely say plot well, actually, it's not a bad idea to plot the log normal, the exponential, and the Weibull all on the same plots. Okay, so I'm going to go backwards one and say, okay, you want to do all three of them and then figure out which of the distributions fits better. This is just basically asking the computer to show you all the distributions, and then show the Weibull with different shape parameters, and then put the actual data that you've collected on the plot and look to see which of those parameters fits better. So you can say, plot my data along with the probability distribution density function and the cumulative distribution function on a plot with the Weibull with these specific parameters, with a log normal and an exponential distribution, and show all of them. And then look to see which one fits the best. So yeah, and that was, by the way, that was my fault here altogether. I actually went and made these plots of some data that I had, forgetting that I actually was looking at the fit to a log normal versus a Weibull, not the plot of an exponential as comparison to a Weibull. But it really doesn't matter, because you can look at all these distributions to see which one fits the best. That's what you want to do. And a lot of times you're going to look at it and go, God, that doesn't fit a normal at all. Well, maybe it fits one of the other distributions. So as I'm saying this, I'm now going to go and jump into the log normal distribution, because now I can jump backwards and show that one to you on a plot. Okay, the probability density function is given right there. Yeah, that's great. What are you going to do? Okay, as you're looking at doing this, you're going to ask the code that you generate to use in Python. You're just going to say log normal, which is the code in Python. Inside the statistical functions, you just say use the log normal distribution for this. Okay. Now, and if you're plotting and you got real data, you can plot it against the log normal. So there are specific things that fit log normal distribution quite well. So if you know something fits the log normal, if you know something fits the exponential, you know something doesn't fit either one of them but might potentially fit a Weibull and doesn't really fit that normal pretty well, you got to look at it. But some things will fit certain things quite well. Okay, and if you look back at the parameters of this, you're going to see that you've got the mu and the sigma, just like you did before. So it really is a log version of the normal distribution. And there's some things that fit it. And sorry about me plotting the log normal versus the exponential, but then talking about the exponential. But that's what it is. And again, that really isn't going to matter a whole lot. So you've got these specific distributions that are the continuous distributions, and these are the ones you're going to use. I mean, really, there are some others that are way more complex. I used a lot of them. I even came up with some of them. But they're good for predicting certain things that you're not going to predict typically in most engineering type problems. So I did predictions of extremal events, what we called extremal events, which means that outliers aren't actually outliers. They're really part of the data because you're trying to predict when something extreme occurs. I was doing weather events. In this case, normal, exponential, Weibull, and log normal are your best ones. Now, as far as looking at the fit, most of the time, I do it by eye. But there are measures of goodness of fit. Particularly the ones that you might use would be Anderson-Darling or Kolmogorov-Smirnov. Not difficult. You can ask when you're doing this. You can say, give me the appropriate goodness of fit of a comparison of this data to a Weibull and an exponential distribution, and show me how well it fits both of those with plots of the data against the actual distribution. And you can make that decision and you can run it directly. And I would say you're going to generate the Python that's going to go ahead and create the plots that you're going to look at by hand. That's how you do it. Okay. Now, how you fit, what I just talked about. One, visually assess it. Okay. There you go. Okay. You do a probability plot. But in this case, I would say, because you're probably not going to sit down and plot these by hand, you're going to tell AI to generate the actual Python that you're going to run to show the data on the curve in the visualization, and you're going to look at it and you're going to use that. But what you're really doing is plotting how well you can you're just going to do a visual assessment. Now, there are goodness of fit testings. Chi-square, Kolmogorov-Smirnov, Anderson-Darling, those are all of those. And you can, and you should actually look at some of those. And I would say, try them. Okay? Try the different goodness of fit and look to see how they actually go against real data. Now, you're also going to look at what parameters you need to actually estimate to do this. Okay, the parameters of each distribution, because there's estimations of parameters. Like when I talked about Weibull, I said you got to estimate that K. And really what you want to do is you want to pick the best distribution to fit the data you have, because now you're going to use them when doing predictions. That's what it's all about, is being able to predict what occurs from those distributions. And the computation, okay, straightforward. You do your PDF, CDF. Well, first thing you typically do is you're going to go ahead and do sampling. You're going to check to see, pick distributions. You're going to see how well they fit based on the parameter estimations and select one. The libraries that are built into Python to help you do this, because it's got a lot of calculations. And the real challenges that you deal with in these distributions, such as distributions, is those numbers, basically what we call the edge cases, or sometimes we call them the outlier cases, those cases that are out there. And being able to make sure, well, one, are those numbers even valid? And does the distribution fit them? Okay. And it is computationally intensive. And I do have a lot of examples that I have given you of real problems that I've solved inside of the Falcon Online. If you're watching this and you're not on Falcon Online, but I gave you a lot of those, and I will, if you need more, I'm going to make more. So your key takeaways: PDF, CDF. That's the basic mathematical framework. Knowing how to select a good distribution to fit the type of data that you have, and then applying it to the scenarios where it applies. That is the bottom line for engineers. So I'm hoping that I didn't confuse you, that you do understand continuous and discrete distributions, how to select them, how to model them, how to plot them, how to look at data against them, because it all boils down to collecting the data, looking at the data, and fitting the data to the distribution that fits it best, looking at the differences between discrete and continuous types of data and fitting those distributions, and then using those distributions to be able to do predictions. That's it for this one. It's a long one. I'm so sorry I made it this long, but I think you're going to need all that information that's in there. Thank you, and I'm out.